All right. Hi again. I'm Martin Becze, and I'm going to be talking about primea. And unfortunately, once again, the logo still doesn't work. But I did have there's a nice primea logo. Anyways, so continuing on from where Alex left off, primea really started with eWASM. And it borrows a lot from eWASM. It builds off the work that eWASM does. It uses the WebAssembly instruction set, and it uses metering, the same metering that eWASM uses. And primea started with eWASM kernel, which was created originally to test eWASM. And then I started experimenting with some ideas with nested contracts and other more exotic forms of communication that didn't quite fit into Ethereum and didn't have a way to be backwards compatible. So that's what inspired it to branch from eWASM kernel. So currently, primea is being developed within DFINITY, and it sits above the WebAssembly instruction set and below consensus. So it's the layer that facilitates inter-process communication for contracts. You can think of it kind of like a kernel. So the problems that it's trying to solve are performance. Current blockchain computers lack performance. Scalability. Trying to fix sort of ad hoc designs. Lots of times we see a lot of recreating things that have already existed in computing for a long time without any knowledge of those things. Not being able to extend. The EVM is hard to reuse and to extend for other purposes than outside of Ethereum. So try to fix that, and provide a greater level of interpolarity. So some solutions that primea offers, and maybe not a solution to solve these problems, but quite a few of them. One thing we change is how contracts communicate, and I'll get into this later. We introduce concurrency, so we can perform parallelism, which helps with performance. And of course, as Alex has told you about all the benefits of eWASM and WebAssembly, we use WebAssembly as our base virtual machine. And lastly, we try to make this general purpose, so it can be used in lots of different places, not just the blockchain even. So I'll get into communication. Communication is what really is different than what's in eWASM or in Ethereum. So communication in primea. Primea provides restricted communication, and I'll talk just a bit more about that later. We also have asynchronous message passing. So there's no synchronous calls. Like in Ethereum, everything's done asynchronously. So what do I mean by restricted communication? Let's say I have 3 contracts here. Authentication contracts, and business logic, and like a database contract. The lines between the circles here represent who can communicate to who. So by default, not every contract can communicate to every other contract. It's restricted. So this allows you to build isolated zones of contracts, and you don't have to worry about them getting attacked or being misused. You can put all your logic that checks for incoming messages in a like authentication module, and then hopefully you can just reuse off-the-shelf components to build the rest of your dApps. Also, since we know who can communicate to who, we can potentially see groups of contracts that are communicating and are mutually exclusive, won't talk to each other. And that allows us to do partial ordering of the messages. So these two groups of contracts, it doesn't really matter what order we run them in because they're not going to communicate to each other. So asynchronous messaging. Why do we want this? The original motivation back when I was working on eWASM kernel was looking at the different sharding schemes. All of them had one thing in common: asynchronous messaging is between the different shards. And I thought it would be good to have a unified set of communication semantics for this. So like your in-shard communications should be the same as your communications across shards. Also, asynchronous messaging allows us, it forces everything to be concurrent, and that enables us potentially to build parallelism, or run these things in parallel. Another difference is things are non-atomic by default. I'll get into this next, but you can have atomicity, it's just not there by default. And we encapsulate our asynchronous message passing in the actor model. So to review, this is how synchronous calling works in Ethereum, and I'm going to explain a little bit of overhead that it introduces. So if contract A calls B, and let's say it's using 100 bytes of registers, then B has to run, but we also have to keep the 100 bytes of registers for A paused. Then when B calls C, C has to run, and we have to maintain B's state also, runtime state, right? So every time we do a call, it introduces more and more overhead that we have to keep around. And then when C is done running, we can go back to B. We can throw away C state now. Now C can finish running. Now we can throw away C state. Now we can throw away B state, sorry, and then go back to A. But every call you do in a nested call, you get sort of an additive growth of resources being locked up. And this problem is a little bit even worse when you have to do with storage and reverts. So the atomicity semantics of Ethereum, so like when A calls B and we mutate A's state, now we have to keep A's old state around. And then when B calls C, we have to keep A and B's old state around, or storage around, right? And then finally C runs, and now we go back to B. And we still have to keep A, B, and C's state all around their storage, right? And then B returns to A, and if A crashes, we have to revert B and C's state and A's state for their storage. So you lock up all the contracts that you touch with having reverts. And that could potentially add a lot of overhead, especially if you do lots and lots of calls. And the way Ethereum limits this now is just to put a max cap on how many calls you can do. And this is 124, I think. But if you eliminated this atomicity and synchronous calling, you could potentially do a lot more calls because, well, there's no overhead. So there's no overhead in doing a call. That means you can have unlimited call depths. So this is what it would look in the asynchronous model. You know, A is running, has 100 bytes, and calls B, and it's just done. Throw it away. And then B calls C, it's done. Throw it away. And then C can return a result to B. B wakes up and runs, and then goes away, and then lastly returns to A. But the problem with that is it's not atomic, and a lot of times you want atomicity. You want to do like book a hotel and a train at the same time. So The way you have to implement atomic databases is usually using some sort of commitment scheme, like a two-phase commit. So instead of doing that for you, we would provide a library that allows you to build this type of stuff on top of asynchronous messaging. And I think we make it fairly easy to, but it would look something like this. Like A is running, it calls B, and then B is going to return a lock to A. And then B will wait, so it'll lock up its state. So you have to manually say, hey, we want to keep this state around. And this way, like, you as a programmer can account for the extra costs if you need atomicity. If you don't need atomicity, it won't have extra costs. So then B, when it's done running and everything is okay, says, okay, I'll commit, and B finally runs and saves the results. And of course, vice versa. If A fails, it can call revert, and B will just throw away its old state. So how do we encapsulate the messaging? We use the actor model, and it's very straightforward. Each contract or program is an actor. Actors have an inbox. They have a mailbox, which other actors can queue messages on. So you see the different actors queuing messages on other actors' inboxes or mailboxes. They have some sort of persistent storage, and they have an address. So it just works like postal service, if you will. And what actors can do is they can create more actors. They can send messages to other actors if they have the actor's address. And they can designate what to do with the next message in their inbox. And that's really what the actor model, core of the actor model is. We do have some differences from canonical actor model, and that is we're deterministic. By definition, actor model is non-deterministic. But we have to have determinism since we want to run in a blockchain. You could loosen that restriction if you're running off blockchain, though. So one interesting fact about actor model is you can't have reentry bugs. So this is where A calls B, and then B is going to call back to A, and now there's a new instance of A running. So instead, with the actor model, what happens is A calls B, and then B calls A, and A's first instance will finish running, then it will get the next message and continue running. So an important part of this is making this deterministic. So we order the messages by how much gas was spent when they were sent. So a mailbox may have a set of messages in them, A, B, C, and it's going to get reordered to a CBA. So A was sent earliest in time because only 25 gas was spent, and then B because 30, and then lastly was 40. So we use gas as approximation of time here. So if gas stands for how many operations can be done in a certain set of time, then you can order messages using that metric. So what happens when an actor is ready to run the next message? It has message A, and it has 25 gas spent. It needs to know if there's any outstanding messages in the system that are possibly older than 25. And the way we do this is maintain a scheduler that keeps track of where all the actors are in time. So the scheduler here knows that actor A has ran for 300 ticks, or 300 amount of gas. Same with B. B knows it's at 200, C at 310, and D at 400. So when an actor is ready to dequeue a message, it asks the scheduler, hey, could there possibly be any outstanding messages older than 25? The scheduler knows that all actors have ran past 25 gas and therefore could not have sent a message earlier than 25, so it's fine and goes ahead and runs it. Now, if the actor had a message of 600, then there could still be messages older than 600. So it asks the scheduler, hey, are there messages older? Could there be messages older than 600? Well, there's several actors that have not ran to the point of 600 yet. Therefore, it could be possible that this actor would get a message older than 600. So it pauses and goes to sleep, and it will wake up once all the other actors have either all gone to sleep themselves or have reached 600 gas. So the last thing I have to say about the actor model is that it has a distributed memory model. It means there's no shared memory in between anything. Okay, so now I'm going to talk about the WebAssembly interface. Okay. So this is how we interact with primea. We have so it's a object-oriented interface, and that means we have objects that the system maintains, and then the eWASM binary references. And our objects are functions, which allows us to make calls to other actors. Data buffer, that allows us to send chunks of data to other actors. An element buffer, which allows us to construct essentially a table of other references. So we could create an element buffer, and it could have functions and data buffers and whatnot in it. A module reference, this is our abstraction for creating new modules, or eWASM modules. So this is what you need to use to create a new actor. And an ID. And lastly, also, so IDs allow you to identify, allows an actor to identify itself. And lastly, links. Links stand for Merkle links and are used in persistent storage. So the system maintains a list of references in an array. It might look something like this. It might have two function references, a data reference, and a link reference. And then the WebAssembly binary would refer to like function 2 with the integer 1, since we're counting from 0. So it's really basic, but that's how it works. So function references. You might have some C code like this. And what a function reference does is allow one binary or eWASM actor to pass a reference to one of its functions, or of another actor even, to other actors. So for example, A might have a function reference to B that points to main. And the system maintains this function reference. And underneath the function reference contains 2 bits of information. The ID of the actor, which in Ethereum is like its address, and the export name or table index of the function. And that way, the system knows when A invokes main on B, this is going to generate a message, and the system will know how to start B up and which function to call. So this gives us something, this also allows us to have mobility. So if A has a function reference to one of the references in C, and also has a function reference to B, what it can do is call B's function reference with the parameter, with the argument of C's function reference. So that allows A to tell B about C. Now B has C's function reference. And this is how all the communication is built up in primea. There's no global communication. Everything is done by passing around these references. That said, there will probably need to be like large registries of other contracts that might want to talk to each other, and you'll be able to look them up. So functions in WASM. The function API looks like this. We have externalize. So that's where we take one function that is in the any func table and turns it into a function reference. So it takes one slot in the any func table, which is the index, and this function will generate wrapper type checking information and put it onto its array of functions and returns the index of the array, which we use as FuncRef. And then you can send that elsewhere. If you get a function reference, you have to internalize it. So given a slot in the any func table and a function reference, this will do the opposite of externalizing. It will generate a wrapper for the function, which when called will create a message in primea to send to the other actor. So this allows you to put a function reference on the table and then use call and direct. So we don't have to introduce a new type of call into primea. We just reuse WebAssembly semantics for calling. Lastly, to adjust how much gas we want to spend when we do the call, you have to set that explicitly. So set gas budget is how much gas you're going to spend when you call this function reference. And it takes in a function reference and an integer, which is how much gas, and it returns a new function reference. And then there's also get gas budget. So given a function reference, it returns how much gas is going to be spent when you call that function. So this is sort of interesting because it allows, it would allow a WASM program to internalize one of its, or externalize one of its functions, set how much gas it's supposed to use, and send it to another actor. And so the other actor can read it and override the gas budget, but it allows other contracts to define how much gas to spend when calling them. Lastly, the other important thing about functions is we annotate them. So in WebAssembly, the only types we have are I32, I64, F32, float32, and float64s. We extend the typing information with our custom objects. So we might have something in C like this function, and it expects a function reference and a data buff. And when this is externalized, this typing information is also captured. So when a FuncRef to foo is called, underneath those are going to be I32s, but it's going to use those I32s as indexes into the reference table and replace them with the actual objects. And we store the custom type information in a custom section in the WASM binary. And it looks just like the regular type section in WASM, except we have a few more integers for our system objects. Okay, I think I'm out of time, but I don't know. I'm going to just finish up this one part. Function annotations, yeah, custom type. And we have to do runtime checking when any func is called. Replace the I32s with the actual objects, and if it wasn't an object in the reference table, the runtime, then it will throw. This is also interesting because this means references Func references are capabilities, if you know, know of capability systems. It's a capability to send a message. And it's also an opaque reference. It's unforgeable. You can't create function reference out of thin air. And lastly, like the other properties of capabilities, it is transferable. So data bus work just like any funcs, or sorry, like func references, except this is for like chunks of data. So you think of it as like a memory section that you can send around, because WebAssembly functions only take in I32s or I64s, floats, etc. If you want to give one function a chunk of data, like you don't want to have it have like 100 I32s. So instead, you create a data buffer, which takes some chunk of memory, puts it in a data object, which you can then send around. Has the internalize and externalize and internalize methods, the same as functions, except instead of reading and writing from the anyfunc table, we read and write to memory. Lastly, it has a length command to tell you how long it is. Elements are also similar to data buffers, except they contain a list of other references. So I can make a element buffer of data of like a bunch of functions, and I could put data buffers in it or whatever. It's really just like an array of references. And this is sort of analysis to what tables do in eWASM, if tables could hold any references. Currently, tables in eWASM only can hold functions, or func. So yeah, it has externalize, internalize, and length. Lastly, there's a module which allows us to create new actors. So given a data buff, returns a module ref. The data buff here is the eWASM binary. Module.self, so if a actor calls module.self, it gets a reference to itself. And then module.export, given a module reference and a name, will return a function reference. Lastly, we have links. Links are used for persistent storage and to represent Merkle links. So link wrap, given any one of the above references, any of the system objects, returns a link. Then unwrap takes in a link and a continuation, which is a callback. And that callback is given the result of looking up this Merkle hash. If you're a LANC client, it might have to go out to the network. It might take a long time. That's why it's a callback. And then we'll return the resulting object. Okay, so I think I'm out of time, way out of time, so I'm going to stop now. But yeah, the same stuff is interpolarity and yeah, extensibility, which Alex also covered. So, all right, thank you.